express gratitude to the organizers for this invitation. I discovered the Combustion Symposium, Mediterranean Combustion Symposium, only in 2017 in Naples, and then again in Tenerife. I wish I had been introduced to it much earlier in my career. It's a venue that I find to be very well organized. There's a sort of a family feel here. Colleagues see each other, care about each other. And so I express my gratitude to the organizers for inviting me back this year. It's a pleasure for me to talk about something that I've been working on for about 30 years. Some of you may be aware of a mentor of mine, Doug Smoot, who worked on coal combustion all of his career, and as part of the center when I was hired after my PhD, I did a PhD study under Ray Visconti, radiation work, and when I joined the faculty at BYU, Doug Smoot had just proposed for a major center, research center, and they needed some help with radiation. And I credit him for giving me my start, and it was this work that we started on, which I'm about to present. We've been working on it, as I say, for about 3 decades, and I developed it, refined it, tested it, and that's what I plan to do today. It goes without saying in this group that radiation is a major component in combustion systems at any scale. It has some contribution, some influence in the radiation, in the combustion work, and it has been the subject. Gas radiation has been the subject of research for the better part of about 7 or 8 decades. And we've made progress all through that time. Today what I want to do is first briefly introduce you to or remind you of the challenge, general challenge in modeling radiation. And then an introduction in the spectral behavior of gases. And all of that is to set the stage to help us understand why it is so difficult to model and do it in a way that can be used in an engineering setting. Then I will survey approaches for spectral modeling of gas radiation, and that will lead me to the focus of this presentation, and that is a global method, the method that we've developed at BYU, the spectral line-weighted sum of gray gases model. I'll show you some model predictions, both in terms of validation results of the model and in terms of application to industrial systems. So radiation transfer is tough. And it's important enough in combustion systems that if it's neglected, you can make hundreds of degrees error in the predicted temperature. It's something that's critical. Solving the radiative transfer is challenging, it's expensive, no matter what solution is what method is used. The radiative transfer equation doesn't show up very well there, but the intensity is a function of 3 spatial coordinates, 2 angular coordinates, and wave number in a steady situation. And that makes it difficult. For example, in one of the commonly used solution methods, the discrete ordnance method, which resolves the radiation intensity by angle, that it requires 4 times the number of angular increments in both the azimuthal and zenith angles. It's that many solutions of the radiative transfer equation. Okay, in 2D, 8 times those the product of those 2 increments in 3D. And in non-gray or band modeling, that's multiplied by the number of bands. And so it's not uncommon in a combustion system simulation to spend 70, 80, 90% of the total computation time on radiation. When we started this, we were looking for an engineering approach. We knew that radiation needed to be accounted for in a realistically accurate combustion simulation, but we wanted to be able to do it in a way that was feasible from an engineering computation standpoint. So without scattering, the radiative transfer equation is written there. Kappa is the spectral absorption coefficient, eta is the spectral variable. Wave number is typically used in gas radiation. That of course can be related to wavelength. The spectral absorption coefficient is defined locally. And for gases, it is dependent on the species present, their temperatures and concentrations, and the total pressure. So whatever model is proposed must be able to devise a scheme for calculating the absorption coefficient locally for input into the radiative transfer equation. What I show here at 4 different levels of spectral resolution is the absorption spectrum for CO2 at room temperature and 1 atmosphere. And you can see on the left panel, there are about 5 bands. These are called vibration rotation bands. And as we move to the right, within each band, you see increasing resolution until all the way to the right, with just a few wave numbers, inverse centimeters, you can see the spectral line behavior. As I say, for CO2, there are about 6 bands of significance, 5 for H2O. The absorption cross-section, which can be related to the absorption coefficient through the molar density and the mole fraction, varies by about 7 or 8 orders of magnitude. Right? Very narrow spectral lines, and doing a line-by-line integration of the RTE, I'll refer to that in just a minute, is virtually beyond computational feasibility, except in very limited situations. The spectral absorption has a very strong dependence on temperature. Here in these 4 panels, you can see CO2 at 1 atmosphere at 300 Kelvin, 1,000 Kelvin, 1,500 Kelvin, 2,000 Kelvin. As the temperature rises, so-called hot lines emerge, which reflect energy transition from non-base room temperature scenarios, and you get a lot more hot lines, a lot more lines that have to be accounted for in applications and temperatures characteristic of combustion. In a typical non-isothermal system, for example, the flame that's shown here, there exists a unique absorption spectrum comprised of multiple gas species of different temperatures, different concentrations, and that spectrum varies throughout the domain. When we began our work about 30 years ago, there was one spectral database for calculating from which we would get line parameters, and that was the room temperature HITRAN database. And we had to calculate from spectroscopic theory the hot lines. Fortunately today, that has been updated. We're about 3 or 4 generations beyond that. And so one can calculate, one can draw on that database to find all of the lines that are included. You can see here for H2O, CO2, CO, the species of principal combustion interest, As the temperature increases, the number of relevant lines, that is the number of lines that contribute significantly to the radiative transfer, increases substantially. Total number of lines in the high temp database for H2O is 111 million. Using a reasonable cutoff that we've used at 3,000 Kelvin, it's about 19 million lines that have to be accounted for. CO2 about 8 million, CO about 23,000. So it's not uncommon to have to deal with tens of millions of spectral lines in a rigorous evaluation of the radiative transfer in gases. High pressure combustion is clearly of interest in the community. So we need to know how pressure affects the absorption characteristics as well. And so you can see for H2O at 1500 Kelvin, the absorption lines, you see the band structure with a much finer resolve, ranging in pressure from 0.1 atmospheres to about 50 atmospheres. You can see the structure is compressed, maxima and minima are minimized. At higher pressure, it becomes more of a continuum structure. Any model proposed has to be able to deal with all of that. So, with that in mind, with that background, all of those tens of millions of lines, when we integrate the radiative transfer equation over the spectrum, we're faced with integration over tens of millions of spectral lines. Okay. Alternatively, we can integrate over a finite spectral range. And I'm going to show you in just a bit what the several approaches are, sort of an evolution of approaches in the modeling of gas radiation over the past 5 or 6 decades. The most rigorous approach is a line-by-line integration. And as I said, it's not uncommon to have 10 or 20 or 30 million lines. Divide those lines into subline intervals, integrate the radiative transfer equation over all of those subline intervals, add them up, and that gives the total radiative intensity. That's simply, those subline intervals are of order 1,000th of an inverse centimeter. This is beyond computational feasibility, except we use it quite regularly for benchmarking models. Okay? Narrowband models, and there's a whole family of narrowband models, take a look at spectral range between 20 and say 50 inverse centimeters and integrate the radiative transfer equation over that wave number interval. And in a typical spectrum, for example, the most well-known, the statistical narrowband model over the 25,000 wave number interval spectrum will use 1,000 wave number intervals. Okay. Wideband models integrate over a yet larger wave number interval, about 500 inverse centimeters. And that brings us to full spectrum, which is the focus of my presentation today. We're often not really interested in resolving spectral variations. Rather, we're interested in many cases in how the radiation transfer communicates to the energy equation. So we're interested primarily in total radiation transfer in the volumetric heating and the energy equation. So by way of summary, line-by-line integration, millions of RTE integrations, very accurate, very expensive. When we first started this 30 years ago with the computer resource of the time, it was taking 2 or 3 days for a one-dimensional simulation, benchmark simulation. We can do it now significantly faster, but still it is not feasible for multi-dimensional situations. As I said, used mostly for benchmarking, comparison with approximate models. Band averaged approaches, thousands of RTE integrations. They are accurate. Rival line-by-line integrations, if done correctly, within a percent or two. And so they can also be used. But they are expensive. Wideband models, tens of RTE integrations, limited applicability to contemporary RTE solvers. Wideband models, they are configured principally for line of sight. And even line of sight along non-isothermal, non-homogeneous, they're very difficult. And that brings us to global models. This requires a handful of integrations of the RTE. So it has promise for a much better computational economy and feasibility in computations of the radiative transfer. The classical weighted sum of gray gas model was first proposed by Hoddle and that was extended by my advisor, Ray Visconti. Modest showed that it has applicability for some certain wall radiative boundary conditions. The Spectral line weighted sum of gray gases model was the first line-based, spectrum-based weighted sum of gray gases model. We first published that in 1994. And the full spectrum K-distribution model of Modest was published shortly thereafter. And those two models have really merged. And fundamentally, theoretically, they are identical in terms of their implementation for gas mixtures and calculation of some of the numerics. It turns out they are, the results are within a few percent. So what I will present here is nominally reflective of the two major global methods that appear in the literature today. So here's our wish list for a spectral gas radiation model. We would like it to be capable to calculate non-gray gas spectral model based on high-resolution spectral data. In other words, capturing the accuracy of the spectroscopic data that we now have access to. For non-uniform, that is non-homogeneous, non-isothermal media, it needs to be able to handle gas mixtures, and it should be able to handle non-gray soot. Okay? It should be accurate. This is our wish list as well. Target accuracy, if we could predict the local radiative heating to within about 10%, then we feel like we do pretty well. Okay? There ought to be some user control on the predictive error, and that was one of our objectives as we started this. And it has to be flexible. It has to be suitable for implementation in any arbitrary RTE solver. Virtually all commercial solvers, all open foam, everything has at least one RTE solver now. So whatever we do has to be easily integrated into those solvers. Has to be easily updated with new spectral property data as it becomes available. Bottom line, simple and fast. Now those are relative terms, I understand. Even with what I'll present, radiation transfer accounting for the spectral behavior of gases can be a significant fraction of the total computation time in a combustion system. So what I show here in the right figure is a sort of exploded view, a high-resolution view of the absorption spectrum. Line-by-line integration would divide that up by wave number and calculate the radiative transfer contribution from each subline interval. We looked at this and said, if we draw a line of constant absorption cross-section or constant absorption coefficient along the spectrum, It intersects all of those lines in hundreds of thousands, perhaps millions of places. Okay? And we said to ourselves, would it be possible, rather than integrating over wave number, to calculate the contribution to the radiative transfer for each chosen arbitrary value of absorption cross-section? And then if we could intelligently choose a handful of those absorption cross-sections and accurately calculate the contribution to each over the full global spectrum, then we could solve the RTE for 5, 6, 8, 10 so-called gray gases, and perhaps capture the accuracy of a line-by-line simulation. So we're effectively integrating over absorption cross-section rather than wave number. So I'm going to integrate the RTE over wave number. In most band model integrations, we can integrate over a spectral band. Okay, as I said, statistical narrow band is about 20 to 50 wave numbers, so wide band is about 500. In the spectral line weighted sum of gray gases model, we're going to integrate over a sum of all wave number intervals. So it doesn't show up very well, but you can see in this top equation, now we're going to integrate the RTE over multiples of wave number intervals corresponding to each value of the selected, arbitrary selected gray gas absorption coefficient. The absorption coefficient can be assumed constant inside each integral. Then the integration yields the gray gas form of the radiative transfer equation, where I sub j is the gray gas intensity, corresponding to all spectral intervals at which the absorption cross-section is C sub j. And if you can do that for 6 or 8 or 10 gray gases, then you can capture it all. Okay? These funny Leibniz terms arise from the interchange of the order of differentiation, that first term, in the case when the boundaries of the spectral wave number intervals depend on position. In other words, in the most generally applicable case, non-isothermal, non-homogeneous, then we have those wave number intervals. We either have to deal with those nasty Leibniz terms, or we have to propose a model that fixes those wave number intervals so that the Leibniz terms vanish in our integration. Now we need to capture from all of those tens of millions of spectral lines, we need to capture the information in a way that is compact and can be easily accessed. And so we proposed a distribution function that we call the absorption line blackbody distribution function. If on the top right you can see a high resolution spectral absorption cross-section at a given gas state, given gas temperature, given a mole fraction for a given total pressure, system pressure, okay? Then on the bottom you can see the Planck blackbody distribution for a given blackbody source temperature T sub B, okay? The absorption line blackbody distribution function is defined as the fraction of total blackbody emissive power at that source temperature T sub B in wave number intervals for which the spectral absorption cross-section is below a prescribed value of C. So if I select in red that prescribed value of C, all of the areas in the absorption spectrum that are below that, we add up all of the contribution from the Planck emission, okay? And if I raise C, you can see that more and more area in the Planck distribution appears. And so the absorption line blackbody distribution function approaches a value of unity, ranges between 0 and 1. Okay? It's a function of C, the arbitrary value of absorption cross-section, the thermodynamic state of the gas temperature, gas mole fraction, and the black body temperature T sub B. Okay? And the relevance of this distribution function will become clear in just a minute. So from the high temp database, we can take those tens of millions of lines and generate a spectrum at each location, then calculate the absorption line black body distribution function for that thermodynamic state at a given black body source temperature. And you can see that I've plotted that for H2O, CO2, and CO at 3,000 Kelvin on the bottom and 1,000 Kelvin, where the gas temperature and the black body source temperature are the same in this case. Okay? You can see that at low values of absorption cross-section, the absorption line black body distribution is small, close to 0 in some cases. As C increases, it approaches asymptotically a value of 1. The ALBDF is higher for CO2 than H2O and higher yet for CO. Okay? When we first started this, we empirically correlated the absorption line black body distribution function using a trigonometric hyperbolic tangent function. And that was so terribly expensive to calculate. At the time, memory was expensive and difficult to access. But as memory became cheaper and cheaper, we were able to use lookup tables. So we have now generated the absorption line black body distribution function over 7 decades of absorption cross-section for a wide range of parameters that are relevant in combustion systems. For H2O, CO2, and CO, black body source temperatures ranging from room temperature to about 3,000 Kelvin in 100 Kelvin increments. Similarly for gas temperature, in 9 different mole fractions for H2O. H2O is a self-broadening species, so you have to account for that. In pressures ranging from 0.1 to 50 atmospheres. And we have tabulated all of that for those 3 species, and it takes about 50 megabytes. And if you look at your cell phone, you'll find that most of the apps on your cell phone take about 3 times that memory. So we can now tabulate, and if I go back to this, you can see that the line tabulated data are virtually indistinguishable from the line-by-line data for the ALBDF. Okay, so this is if we can neglect the Leibniz terms, if they're ignored, or we can rigorously eliminate them, and we integrate the radiative transfer equation, we get on the right the gray gas form of the radiative transfer equation. And kappa sub j is the gray gas absorption coefficient from among the handful that we will select. And A sub j represents the weight or the contribution of the total radiative transfer for that gray gas. So if we can calculate kappa sub j and A sub j, then we can solve the radiative transfer equation a handful of times and hopefully get accurate results. I'll show you some. We simply sum them over all gray gases. We have to be able to handle gas mixtures. For a mixture of gases, the absorption coefficient is a superposition of absorption spectra of all mixture components. Okay? And there are 2 approaches. The ALBDF can be generated and tabulated for all possible combinations of gas species, all mole fractions, all gas temperatures, at all pressures of interest. My friend and colleague Mike Modest has taken that approach. It's about between 5 and 7 gigabytes of memory. Very accurate. We took another approach. We investigated 4 possibilities for calculating the absorption line blackbody distribution function from the separate ALBDF of each species. And among those 4, we have found that the multiplication approach, much, much faster, requires far less memory than option 1. As I mentioned, 50 megabytes. And it produces results that are within a few percent of the more rigorous option 1. Okay, so this demonstrates the construction of the spectral line weighted sum of gray gases model. Again, what we're looking to solve is the gray gas form of the RTE, and so we need to calculate, we need to determine the gray gas absorption coefficients and the gray gas weights, kappa sub j and A sub j. So the first approach is to select a gray gas absorption cross-section from which we can calculate the gray gas absorption coefficient. And in principle, in practice, typically what we do is specify a couple of bounding values of the absorption cross-section, and the gray gas absorption cross-section is some average. We use a geometric mean. That selection then specifies the spectral intervals. From the spectral intervals, then we can calculate the gray gas weights. Okay? We solve the RTE, 1 for each gray gas, with input for each gray gas absorption coefficient and weight, corresponding weight. And that gives us the total intensity. In uniform media, that is where temperature is uniform, concentrations are uniform, it turns out we've shown theoretically that this gives exact results. This gives line-by-line results if sufficient number of gray gases is used. And therefore, one has control over the accuracy by specifying the number of gray gases. Okay. What I'm showing here is a result for 25 gray gases. There's virtually no difference. The real problem that we face is for non-isothermal, non-homogeneous media. Because as I mentioned, the absorption spectrum varies with location. So integrating the spectral RTE over all those wave number intervals yields those nasty Leibniz terms that we have to deal with. This is true unless the spectral intervals remain constant from one location, spatial location, to another. And so we explored possible ways to handle that. There are sort of 2 classes of approaches. One is the scaled spectrum approach, and the other is the correlated spectrum approach. We've investigated both and have sort of put all of our money in the correlated spectrum approach basket. The correlated spectrum assumption relates the spectrum at one thermodynamic state in the domain to that at another state. And this approximation preserves the spectral intervals of integration and eliminates the Leibniz terms. It does represent an assumption, an approximation. And we have found theoretically that there are 8 possible correlated approaches. And all of the spectral line-based global methods can be related, are included in one of those 8. Okay. I'm going to only mention 2 here. The reference approach was our first back in the 90s, and the rate correlated approach was published about 8 or 10 years ago. In the reference approach, I won't go through this, you can read the literature. It requires user specification of a reference state, a reference temperature, a reference mole fractions, etc. And it requires at each location 3 evaluations of the absorption line blackbody distribution function. One of those is an inversion, which can be costly. Okay. The rate correlated approach, on the other hand, requires no specification of a reference state. It uses a reference spectrum, an arbitrary reference spectrum, and only 2 ALBDFs are required. Okay. And our testing has found that it's faster, it's much more robust, and generally speaking, the most accurate of all of the 8 possible correlated approaches. If the media are strictly correlated, spectrally correlated, as is shown in this case for an isothermal domain with CO2 that is not a self-broadening species, then the spectral line weighted sum of gray gases, the rate correlated approach produces exact results if sufficient number of gray gases is used. That doesn't happen very often in practice. Now, how do we handle soot? Okay, the absorption coefficient for soot spectrally is a function of wavelength or wave number, and that function depends on the complex index of refraction for soot from the solution to Maxwell equation. A common modeling approach is to assume that soot varies inversely with wavelength, or linearly, in other words, with wave number, proportional to the soot volume fraction and some constant C that is unique to each fuel type. So what we have proposed is to generate an absorption cross-section for soot, calculate the absorption line, an equivalent absorption line black-body distribution function, and treat it as a pseudo-gray gas. Okay? This can be done, I show it here for linear wave number dependence, but it can be done with any wave number dependence for soot, any sophistication of modeling. So then we can treat soot as another gray gas in the multiplication approach for gas mixtures. And what I show here is parabolic temperature profile, concentration profile for CO2 and H2O, and 2 different mole fraction distributions for soot. The error between the line-by-line, or rather the statistical narrowband result and the SLW model results are due solely to the error in modeling the gas. There is no error in modeling the soot. Okay, so let me show some results. These are benchmark results compared with line-by-line simulations in one-dimensional situations. So a parabolic temperature profile between 500 and 500 Kelvin, parabolic concentration profiles for H2O and CO2. The black line is the line-by-line, and you can see 3 of the possible 8 correlated SLW models. In general, the rate correlated model is more robust, it's more accurate. The line-by-line prediction required 22 hours, and we were able to calculate the flux divergence, the local radiative heating, in a couple of seconds using the SLW model. The trade-off between accuracy and computation time is user controlled through the number of gray gases. So I show this. This is a study from a colleague of mine who implemented. We helped him implement the SLW model, comparing the Planck mean, which is a commonly used rudimentary model in radiation calculations in a one-dimensional situation, and you can see that the Planck mean absorption coefficient exaggerates the radiative heating. In this case, the classical weighted sum of gray gases model and the rank-correlated SLW model are very close. And the rank-correlated SLW model with 4 gray gases takes about twice as long as the classical weighted sum of gray gases model. This shows an example of an implementation in an industrial setting. In this case, a glass furnace, an end-fired glass furnace, 300 ton, 12 meters long, 8 meters wide. The simulation was calculated using a rudimentary radiation model, and then all of the concentration and temperature fields were frozen. And along those 4 lines of sight, the radiation was calculated using a reverse Monte Carlo, demonstrating that we can implement the model in just about any radiation solver. And on the bottom, you can see the bottom graph, you can see the error relative to the maximum weighted sum of gray gases model, the coefficients from board bar, about 35% error, maximum error. And the rank correlated model is as close to the CK model, and L distribution model is I won't say much about that except that it's a benchmark, a near line by line benchmark accuracy. Let me show a couple of cases where the SLW model has now been implemented in a comprehensive combustion simulation. This is drawing from a work from our colleague Jean-Louis Consaldi. And I've pulled one case out. This is a hydrogen air flame. And I chose this because it shows 2 different pressures. 1 atmosphere, 30 atmosphere. It's turbulent axisymmetric diffusion flame with turbulence radiation interactions. The H2, the hydrogen jet diameter is 3.75 millimeters, and the velocity is just under 300 meters a second. And there's co-flowing air at meters per second. And you can see 1, 2, 3, 4 different radiation models with all other transport and reaction models being the same. The FSCK 1, 2, and 3 models are identical theoretically to the rank-correlated reference approach, the reference approach, locally correlated, and rank-correlated models. So, and the reference is a statistical narrowband correlated K with about 1,000 bands. And you can see that it's a little hard to see. The reference approach suffers from pretty significant error. The rank-correlated approach, the error is less than 5%, maximum and mean error is less than 5% in all cases. And finally, this is a case from our colleague Klaus Anderson, an oxy-fuel combustion case, recirculated exhaust gases with a primary lance and swirled oxidizer streams. And we used this as a test bed to see how many gray gases we could get away with. Okay. So what you see on the bottom is what we call a disparity map. It's the temperature predicted using a rudimentary weighted sum of gray gases model with the rank-correlated SLW model. Those are differences in temperatures. And you can see that predictions in and near the flame zone can be about 300 Kelvin off, 300 Kelvin error. And in terms of radiative heating, you can make locally errors of about 800 to 1,000 kilowatts per meter cubed. And this demonstrates the dependence on the number of gray gases. So the left panel is temperature, the right panel is radiative heating. And on the top half of the top left panel, you can see the rank-correlated model with 5 gray gases. On the bottom, it's 10. And on the panel on the bottom, you can see 3 gray gases compared to 10. Similarly on radiative heating, and there's very little difference between 3 and 10 gray gases, virtually no difference between 5 and 3. And this confirms our one-dimensional studies that demonstrate that it's you can get accurate results with as few as 3 to 5 gray gases. So let me conclude. Gas radiation is tough. Presents a challenge in the prediction of radiative transfer, and relative to our wish list for developing a model, the SLW model is capable. We can do real gray gas behavior in non-isothermal, non-homogeneous gas mixtures with non-gray soot. It's accurate. A maximum error in local radiative heating, which is the most unforgiving metric in all of these predictions. Maximum error is typically less than 10% and usually within a handful of percent relative to line by line. It's easily integrated in any RTE solver. I had an undergraduate student implement it in Fluent. It can achieve accuracy approaching line-by-line calculations at a very tiny fraction, 10 to the minus fifth of the computational cost. And a colleague of mine in the combustion group at BYU, with our help, developed a code, library code for those who wanted to use it to call in implementing in their combustion mods. So at this point, I'll thank you for your time and interest and for not falling asleep after lunch.
Thank you so much for that really interesting presentation. Yes, please, questions? Maybe.
Thank you, Professor. A very, very insightful presentation on radiation. My name is Soumitra. I work with Professor Roberts and Basim Delhi, CCRC. I have interest in industrial furnaces and boilers and big setups where traditionally we have used heavy fuel oil. And there the radiation heat transfer is the primary mode. Now there are discussions and thoughts about having co-flow ammonia or hydrogen with those kind of fuels. So what are your thoughts about radiation heat transfer if we replace these fuels by hydrogen or ammonia? What will happen to that?
I actually had this thought this morning when we heard that nice presentation. I'm not sure I'm in a position to really speculate, but I believe, I'm quite confident that we could model it accurately with the SLW model, with ammonia, co-flowing ammonia. One of the things that we haven't done that probably could be done is to develop ALBDS for methane and for ammonia to calculate the radiative preheating prior to ignition. That would be a great thing to do. Let me know when you have it done.
Hello, my name is Victor Scherer from Bochum University in Germany. Really, I loved your presentation. Thank you for summarizing the status of radiative heat transfer for gases. My question is a little bit, are there any limitations of your method where you would say, be careful in using this kind of methods?
If your application has non-gray boundaries, then we're in trouble. Then we've actually extended the SLW model to non-gray boundaries, but then it requires spectral bands corresponding to each of the gray boundary bands with ALBDF generated in each spectral band. So it can be done, but it just increases the cost. In terms of other areas, of course, when you have the continuum radiation of particulates, I'm not sure you need the sophistication of a gas spectral property model. All of you probably know that. You can use whatever is simple because the particulates are going to dominate. Other cases, we have done some pretty significant and exhaustive testing over a wide range of temperatures, and this may sound like a sales job, but we're pretty confident that the used reliably in the combustion applications that we have faced so far. The ones in the future, we'll have to wait and see. Good question, thank you.